Okay, in this video I'm going to explain how to use the Pico NVH Diagnostics kit. This is basically an interface that connects between your picoscope and either a microphone or an accelerometer so that it can measure noise or vibrations, and it sends it to your picoscope and we use the software to analyze it. And essentially all this system does is it picks up the frequency of these noises and vibrations and it compares it to the frequencies of the other components on your car, the moving components on your car, like the engine or the pulleys or the wheels or axles or drive lines. So this is the interface box right here. It connects to channel B on your picoscope, and on the other end you'll connect the microphone or accelerometer. We also have a 3-channel interface as another option, and it allows you not only to pick up the vibrations but to determine the direction of the vibration, either on the X, Y, or the Z axes of the vehicle. And to be honest, I don't use that feature a lot. I am more interested in the general vibration and in the amplitude and frequency of those vibrations. This is the accelerometer that would connect to this interface. It has a magnet on the end, and it also comes with a little cover, protective cover on the end of the magnet. You'll need to remove that so that it will stick to the metal on the vehicle, and it attaches to either the seat rail or the engine or whatever component it is you want to measure the vibrations. This is the microphone. The microphone screws onto the end of the cable and then connects to the interface. Now your picoscope needs to be NVH enabled. So when you buy one of these NVH kits, they send you a code that you can enter into your picoscope. Connect the picoscope to your laptop and it enables this Pico to operate with the NVH kit. If you have multiple picoscopes, this kit will not work on all of the scopes. It only works on the one that you enable. Okay, we're going to connect the NVH interface to the picoscope, and it needs to connect onto channel B using this BNC cable that comes with it. If you're using the 3-channel interface, we would connect that to channels A, B, and C. Okay, now we'll connect the microphone or accelerometer to the interface. So the cable connects here, and once you connect the cable, you should see the little red LED on the back of the interface begin to flash. Which indicates that your battery in the interface is good. If not, you'll need to replace the battery. And now I'm attaching the microphone to the end of the cable. We would connect the accelerometer in the exact same way. Okay, the next thing we'll need to do is we need to connect our laptop to the OBD2 data stream of the vehicle so that we can get the vehicle speed and the engine RPM from the vehicle. That's how the software compares the frequency of our noises to the frequency of the components on the car. This first one is a Cardac M sold by Drewtech. This second one is a Mongoose Pro ISO CAN 2. Now, both of these devices require an additional driver that you download from the Drewtech website. This third one is a generic LM327. If you try to buy these, you'll find that they make a lot of knockoff versions of LM327s, and they don't work. The Cardac itself costs about $1,600 or $1,700. The Mongoose probably cost $300 or $400, but this generic LM327 cost me about $40. Now I had to search pretty far and wide to find a genuine LM327. You can see that this one is I'm not promoting any specific company or website, but I found this one at totalcardiagnostics.com for, I can't remember, maybe around $30 or $40. And so far it has worked on every vehicle that I've tried it on. The Cardac M seems to work on all vehicles. The Mongoose Pro for the ISO CAN only seems to work on vehicles that are CAN enabled, so they use the CAN communications network. That would be 2008 and newer for most vehicles and a few older vehicles. So anyway, if you're on a budget, this is the one that I would definitely recommend. Okay, now we've got this connected in the vehicle. We have the microphone there, and we have the NVH interface connected to channel B on the picoscope, which is connected to our laptop via the USB cable. On the other end, we've connected our LM327, and we're going to plug that into the data link connector. Now typically for mounting a microphone on the interior of the car, you're going to want to place it near to where the driver's ear would be. So maybe you would mount it here near the headrest so that it picks up the sounds that the driver would be hearing. If you're going to be using the accelerometer to pick up vibrations on the interior of the vehicle, you might want to place the accelerometer on the driver's seat rail. That way you'll be picking up the same vibrations that the driver would be feeling when he's sitting in the seat. And if you're only measuring vibrations on a single axis, the orientation of the accelerometer doesn't really matter. Okay, now that we're connected, we need to open up our Pico Diagnostics software and then click on the NVH tab, which opens up this application, and we'll have the option to start a new test. And it's going to ask us how we want to connect to the OBD2 data of the vehicle here. So I'll just select Next. Mine, for some reason, wants me to have the Cardac M connected, so I'm going to cancel that. There we go, it just connected. You'll notice it's going to ask us several questions about our vehicle. We need to fill these out so that it can help us to identify the components on our car causing the noises and vibrations. If you have any noise that may be coming from the drivetrain, like the differential or the drive shaft, you'll want to make sure to put in the rear differential ratio. If you don't know it, you can look it up in your service information. You can also find this along with your gear ratios pretty easily, usually by Googling them or looking on Wikipedia. If you know the exact model of transmission that you have in your vehicle, for example, you can type it into Wikipedia, and it usually has the gear ratios of that transmission in there so that you can input this. You need the tire size. If you're going to be dealing with anything related to vehicle speed, put the tire size in here so that it can calculate the number of tire revolutions per second. Choose which interface you're using. And if you're going to be using the microphone, it only uses one axis. So even if you have this 3-channel interface, make sure that you select the single channel interface. Otherwise, it won't let you select microphone over here on the drop-down menu. So here's where we would select our microphone or accelerometer, depending on the device or the sensor that we're using. This shows us how to connect it again. We've done that already. You'll notice the little green bar moving too. That shows that we are picking up sounds. Okay, now it takes us over to this Record and Analyze tab. We're ready to record, other than I'm going to go back to this Vehicle Information tab and show you where we can review what we've inputted here, and we can input more information. If we're looking at any noises or vibrations that might be coming from the transmission, we should put our transmission gear ratios in right here. We should also make sure that we have the correct rear differential ratios again. If we're looking at any noises or vibrations that are coming from the engine, maybe a pulley or a belt, we should measure the pulleys and input the sizes of those pulleys into this system so that we can identify a noise or vibration coming from one of the pulleys that are driven by the belt. Just as a note, we could log other data PIDs along with this information as well if we want to. I have never found a need for that myself, but you could log something such as mass airflow or temperature or other PIDs. Okay, so now we're back to the Record and Analyze tab. We come down here and click Start Recording. Along the bottom here is, this graph along the bottom is going to monitor our sounds or vibrations over time. So I'll click Start Recording, and you'll notice that it's recording sounds right now. It's picking up the sound of the microphone. And we have, by default, 50 seconds to record, and that's all. You'll see along the bottom. There's a way to change that, and I'll show you that in just a second. Up on the top here, we are looking at something that's called spectrum analysis. And so it has frequency along the x-axis rather than time. And so it's analyzing what it's seeing down below on a frequency spectrum analysis. And we're looking for the high points. Those would be the loudest sounds or the biggest vibrations. You'll also notice that we see this E1 and E2 appearing. The engine on this car is running right now, and so it's creating these vibrations. And E1 means it's a first order engine vibration. It means it's happening at exactly the same frequency as the turning of the crankshaft. So whatever the RPM of the engine is, you divide that by 60, and that tells you your frequency of your crankshaft. E2 is something that's happening twice as fast as the crankshaft. It's called a second order vibration or a second order noise. And that's actually common. On a 4-cylinder engine, you should have 2 combustion events for every revolution of the crankshaft. And so you really should have E2 as probably the loudest noise or the strongest vibration coming from a 4-cylinder engine. If it was a 6-cylinder engine, an E3 or a third order vibration or noise would be your strongest vibration or loudest noise. So that's what the E2 and the E3 and the E1 represent. If we had added tire sizes and differential ratios, we would also see T1 and T2 for a first order tire vibration or a second order tire vibration or tire noise. We could also have a P1 or a P2 representing a propeller shaft vibration, or it could help us to identify an alternator noise or something else if we had put that information into the vehicle information up here. It'll have more of these that show up. Okay, you'll notice that the left-hand column over here is in decibels. That's the amplitude of a sound wave. Sound pressure level is measured in decibels. The louder it is, the higher the number of decibels. So we're generally looking for this point here that has the highest decibel level, or the highest amplitude. That's the loudest sound. And then we're going to want to identify what the frequency is, and so we can figure out what might be causing that sound. I'm going to rev the engine here. You'll notice as I do that you see the E1 and E2 moving to the right. That's because the frequency of the engine is increasing. As the RPM increases, the frequency increases. And then I decelerate and it comes back. So this scope has the ability to detect the frequency of my engine, of my tires and wheels or drivetrain components, and then compare that to the frequencies of the noises that I'm picking up. You'll see down here along the bottom that's recorded this. And the blue line represents my engine RPM. You'll see where I revved the engine just a minute ago. I can drag this little window across. And as I drag the window across, it only analyzes the portion of the waveform that's highlighted by that blue window. During this time that I have highlighted right now, this is my frequency spectrum analysis. Okay, so by default it only records for 50 seconds, and after 50 seconds it'll start to write over top of what it's already recorded. So if you need to record for a longer period of time, you come up here to Options, Advanced Options, and then come down here to this Features tab. And you'll have to click on Enable Advanced Features. And I know that this is something that you probably wouldn't find on your own. That's why I want to point this out. Once I enable Advanced Features, I'll come back over here to Setup, and now this appears. I have signal options, and so I have a maximum signal history size. And I can increase that up to 500 seconds, which is a little over 8 minutes. And that's the maximum time that I can record for. While I'm here, you'll also want to notice that if I go over to the Graph tab, that my maximum frequency of interest is at 200 Hertz. And that's fine for low frequency noises that come from my engine and my drivetrain and so forth, ticks and knocks, tire noises and drivetrain noises. But if I'm listening to a noise or vibration that is a high frequency, maybe a squeal or a whining type of a noise, I will want to increase that frequency so that I can pick that up on my frequency spectrum analysis. Okay, now I'm going to show you a couple of examples of how to use this. This is a noise recording that was taken from a vehicle right after the engine was rebuilt. This had a knocking noise in the engine, which of course isn't a good sign, but we decided rather than just tearing the engine down to find out if I had a rod bearing or something else, we wanted to try to identify the component or components causing this noise. So I took this recording. I can move this window across here, and you can see from the blue line that this is where the engine was started. I want you to notice also that I can play this back. So if I place this here and press the play button, we can hear the sound. I don't know how well you can hear it, but it had a knocking noise in the engine. Now I can move this across and analyze, but basically you'll notice that this engine just idled the entire time, so I shouldn't see much difference anywhere that you place this. I also want to point out that if you wanted to analyze this over a wider time period, you just stretch this out a little bit. Okay, so what I want to do is come up here to this spectrum analysis, and I have several options, but the very first thing that I want to point out is you're always looking for the noise or vibration that has the highest amplitude. In this case, there is a clear point that has the highest amplitude, and that is an engine third order noise. So in other words, a noise that is occurring 3 times as fast as the crankshaft. Now this happens to be a V6 engine, and so that is normal to have a noise like that because there are 3 combustion events for every revolution of the crankshaft. However, this is a very high amplitude, quite a loud noise. So this is that knocking noise that we're picking up, and we could mark off the frequency. We can see that the frequency of the engine or crankshaft is 20 Hertz, which translates into about 1200 RPM here. And this should be about 3 times that. So right around 62 Hertz is when this noise is happening. Now in this particular case, the picoscope isn't pointing out to us what causes this. Now you can click on these and it gives us some hints here. It says this is a normal engine noise or vibration, but there's nothing here that's telling us what component this is. So with a little bit of thinking, we started wondering what happens at 3 times the frequency of the crankshaft. And after doing a little bit of thinking and talking to the students who rebuilt this engine, we realized there were 3 torque converter bolts on the flex plate of this vehicle. And so we had them check that, and sure enough, they found that they had left the 3 bolts loose, and so as the engine was turning, those 3 bolts were hitting the engine, causing this engine third order noise. Not a difficult problem to fix. I'm glad that we were able to use this tool to prevent them from having to tear the engine down. I also want to point out that there are some other options here. I like this bar graph. It helps us to see the orders of the different noises and to see which one is loudest if you're having a hard time determining that. So this bar graph is a nice way to look at it. I also want to point out that we can add a vibration. So if I wanted to turn on or off my engine first order, second order, third order, and so forth, or create a new one. If I was suspecting that a noise was coming from the camshaft, it would be an engine 0.5 order, so I could turn this one on. Once I turn that on, you'll see that it shows up over here. And of course, we don't have a noise coming from our camshaft, so we don't see a spike in that area. Okay, so now I have one more case study to show you. This is a vehicle that had a vibration at 45 miles per hour. It would seem an awful lot like a tire vibration, but this car has been to the dealership several times. The tires were balanced multiple times, and this vibration persisted. So down here we can see that we have extended our time so that we recorded for more than just the 50 seconds. And this is no longer measuring sound, but vibrations. And so you'll see now the amplitude is in millig's. A g is the acceleration of gravity, which is 9.8 meters per second squared, and these are millig's. And typically, as a rule of thumb, from the interior of the vehicle, we don't want to ever have a vibration that is stronger than about 10 millig's, or it's going to become a complaint. So you want to keep the amplitude of your vibrations under 10 millig's on the interior of the car. As we come down here and look at the bottom, we'll see the blue line, which represents the engine RPM. So you can see that the car is being driven here. And the red line, which represents the vehicle speed. You'll see the axis labels over here on the side. You'll also notice all of these numbers and an N. That's because in this case, when we set up the vehicle information, all the gear ratios were inputted into these fields, as well as the pulley diameters. We also have the final drive axle ratio. This is important. If you don't know where the vibration is coming from, you're going to want to put as much information in as you can. And so, based on the difference between the engine RPM and the vehicle speed, this software is able to determine which gear we are in and when, so you can see our shift points. And that's kind of neat. We can tell what gear we're in. Okay, since we know that this vibration was occurring at 45 miles per hour, we're going to want to bring this little window over here to a time when we're going about 45 miles per hour. Looks like there's 50 right in that range. At 45 miles an hour, when the driver is feeling this, we'll want to look at our highest vibrations and first of all see if any of these are above 10 millig's. So 10 would be right about there. And it looks like we have 2 very strong vibrations that are significantly above the 10 millig's. And as we look at these spikes, we can see right off the bat that they're related to a tire. So this is a T1, a first order tire vibration, and this one here looks like it's a T2 or a second order tire vibration. So that's pretty easy. There's not a lot more to do. We've got a tire or an axle or something along those lines that's spinning at that same frequency causing this. Just to let you know what happened, it turned out that there was a bad tire on this vehicle. it needed a road force balancer in order to detect that it had excessive road force. It wasn't just a matter of balancing the weight. It had two parts of the tire that were stiffer or had more force, causing a strong T1 and T2 tire vibration. And without this tool, it would have been very difficult to find this problem. So there are a couple of examples of how you'd use this. I hope this helps. I hope this gives you the confidence to go grab the tool and set it up and use it and experiment with it. It's a really amazing tool once you understand how to use it and get comfortable with it.